Welcome to this video, which is an introduction to scientific notation. Let's begin. Before you can understand scientific notation, you must understand what it means to have a place value number system. To better understand our base 10 place value number system, let's compare it to Roman numerals. Roman numerals use different symbols to represent different values. For example, I means 1, X means 10, and C means 100. These symbols have the same value even when their location changes. For example, I means 1, I means 2, I means 3. All of these symbols have the same meaning regardless of their location within the number. Let's compare this to a base 10 place value number system. A place value number system uses different symbols and different locations to represent values. For example, if I write just the number 1, it means 1. However, all of a sudden, if I write 1 and then put a 0 next to it, or if I put a 1 next to it, or a 2 next to it, or a 3 next to it, or any other number to the right of it, then it changes its value. All of a sudden, this digit that's still a 1 doesn't mean 1 anymore. What does it mean instead? It means 10. Likewise, if I put 2 digits to the right of the 1, it doesn't mean 1 or 10 anymore. Now it means 100. So as you can see here, 1 means 1, 1 we actually read as 11, and 1 we read as 111. So again, the same symbol can have different values depending on its location. And that's what a place value number system in general does, that a different system like a Roman numeral system does not have. All right, let's do some examples. When we multiply by powers of 10, we move the decimal place to the what? We move it to the right based on the number of zeros. So for example, if I have 6.2 times 10, 6.2 times 10 is 62. I move the decimal point to the right one time. In scientific notation, I would write that as 6.2 times 10 to the first power. What if I multiplied 6.2 times 100? Well, I would move the decimal over not once but twice, so it would become 620. And if I wrote that in scientific notation, I would write it as 6.2 times 10 to the second power. If you're wondering where the second power came from, well, 100 is, by definition, 10 to the second power, right? Another way to think about it is that 2 is telling me that I moved my decimal place over twice. What if I have 6.2 times 1,000? Well, you can type that into your calculator, or you can move the decimal place 1, 2, 3 times, fill in the blanks with zeros, and you will see that you get 6,200. How would I write that in scientific notation? Well, I would write it as 6.2 times 10 to the third power. So 10 to the third power is telling me a few things. One is it's reminding me that I moved my decimal not once, not twice, but 3 times. Also, 1,000 by definition is 10 to the third power. If you don't believe me, type 10 to the third power into your calculator or compute 10 times 10 times 10. 10 to the third is 1,000. So, in general, multiplying by positive powers of 10 makes numbers larger. All right, let's keep going. What if instead of multiplying by 10, we divide by 10? Well, when we do this, we're going to move the decimal point to the left based on the number of zeros. So you can type into your calculator 6.2 divided by 10. Okay, when you do that, you should get 0.62. So another way to do this is to think about this as moving the decimal place over 1 unit. So dividing by 10, you might recall from a previous section that we learned, right? So if we have 6.2 divided by 10, well, that's 6.2 times 1 over 10. And remember, 1 over something is the same as that value to the negative first power. Okay, so we're actually using the definition of negative exponents here to write these numbers in scientific notation. So again, if I have 6.2 divided by 10, that's 0.62. Okay, and this dividing by 10 translates to multiplying by 10 to the negative first power. What about 6.2 times 100? Well, you could think of it as moving the decimal place to the left not once, but twice. So I would have 0.062. Okay, and that's how I would write it in standard notation. Okay, but we also know that dividing by 100, right, is the same as doing what? As, well, first let's rewrite it as 10 to the second power, right? So 1 over 100 is 1 over 10 to the second power. So that's going to become 10 to the negative second power. So we have 6.2 times 10 to the negative second power. All right, then last but not least, we have 6.2 divided by 1,000. So again, we're going to move the decimal place over 1, 2, 3 times. Okay, so in standard notation, that is 0.0062. Okay, so how could I write that in scientific notation? Well, we have 1 over 1,000, right? Because we're multiplying by 1 over 1,000 or dividing by 1,000, same thing. Well, that's 1 over 10 to the third, which is the same as 10 to the negative third. So in scientific notation, that is going to be 6.2 times 10 to the negative third. So when we divide by powers of 10, remember that's the same as multiplying by negative powers of 10. And this is making the numbers smaller. Notice the pattern as we go from here to here and here to here, our numbers are getting smaller and smaller. So now we have enough context, enough application to think about and introduce scientific notation. So the answer to the first two questions, what is scientific notation and why do we use it? The answer is actually the same for both questions. The scientific notation is a shorthand method for expressing very large or very small numbers. Okay, so that is what it is, and the reason we use it is exactly the same as the definition, right? We do it so that we have a shorthand method for expressing very large or very small numbers. And the reason it's called scientific notation is because we use it the most often in science. So if you think about maybe you're studying astronomy, right, and you want to measure the distance from the sun, so from the Earth to the sun. Well, that's 92.96 million miles. So you could rewrite that in scientific notation. If you wanted to think about the mass of the Earth, the distance from Earth to Pluto, Avogadro's number, which is the number of atoms of 1 mole in 1 mole of a substance, all of these are very, very large numbers and are typically expressed in scientific notation. But in science, right, we also zoom in really close and we look at things that are very tiny, that are invisible to the naked eye, like the size of a cell, right, in a plant or an animal. Or we could look at even smaller than that and go down into an atom, and then even smaller than that and look at the parts of the atom. So the charge of 1 electron is very small. The wavelength of light, the diameter of a water molecule, all of these are very, very small things. So again, in science, we have a great need to express very large numbers and very small numbers in a more concise way that just makes them easier to write and express. So scientific notation looks like this. It can be a positive or a negative number. So we say it's plus or minus a times 10 to the n. Okay, and a, this has a special name, if you want to know. It is called the mantissa. Okay, so the mantissa has to be at least 1, but it has to be strictly less than 10. So by definition, how many digits can be in front of the decimal point in order for a number to be in scientific notation? Okay, the answer is just 1. Okay, so let's do some examples. If I have 2.67 times 10 to the third power, okay, is that in proper scientific notation? And the answer is yes, because you only have a single digit, right, which is greater than 1 and also less than 10. Okay, so 2.67 times 10 to the third power is an example of something that is in proper scientific notation. What if I have 0.7 times 10 to the third power? Okay, now we have a problem because we're violating this rule. Remember, our mantissa, right, this digit has to be at least 1. 0.7 is smaller than 1, so this is not in proper scientific notation. So on a test or a quiz, homework assignment, if you wrote that as your final answer, you would lose points because you have to do a little bit more work to get it into proper scientific notation. Okay, what if I have 15.273 times 10 to the negative 10th? Is that in proper scientific notation? Well, the answer is no, because why? Because we have not 1 but 2 digits in front of our decimal point. In other words, our A is not strictly less than 10. So this is another example of something that is not in proper scientific notation. So if that was the result of a computation you did, you would have to do a little bit of extra work to convert it into proper scientific notation. What about 1 times 10 to the 7th power? Is that in proper scientific notation? Absolutely, right? Because we only have the 1 digit and it's at least 1. So we have 1 times 10 to the 7th power. Okay, so those are some examples of values that are either are or are not in proper scientific notation. And I'm just rewriting my multiplication as a star just to drive home the point that it is multiplication and not a second decimal, which would look weird. Okay, so I strongly encourage you at this point to pause this video and complete the following exercise to review what you've done. Right? And all you're going to do is either check, yes, this is in proper scientific notation, or no, it's not. Okay? If you say no, okay, if you said no to this problem, then you have to explain why. Why is this not in proper scientific notation? So pause this video, work through these problems, and then unpause it, and I'm going to go through these answers. Okay. So the first one is not in proper scientific notation because 0.7 is less than 1. Remember the mantissa, this is the mantissa, it's the number next to the power of 10, has to be at least 1. Okay, the next one, it is in proper scientific notation, so give yourself a pat on the back if you said that. The next one is not in proper scientific notation because 66, the mantissa, is larger than 10. It has to be strictly less than 10. Okay, and last but not least, again, this is not in proper scientific notation because once again, the mantissa is smaller than 1. Okay, it has to be at least 1 and has to be strictly less than 10.